class, we are now on 9.3, the shapes of molecules. The shapes of molecules critically affect their properties. For example, when we breathe, our bodies expel two compounds, carbon dioxide and water. Both are small, simple molecules, but CO2 is a gas at room temperature and water is a liquid. Why the difference? Well, as we'll see in lessons ahead, the shape of the molecule plays a big part in determining these properties. Fortunately, we can use Lewis structures to predict the shapes of molecules. To do this, we use an approach called valence shell electron pair repulsion, or VSEPR model. The key idea behind this model is that groups of electrons repel each other. That is, they want to be as far away from each other as possible. In order to use VSEPR theory, we must be able to draw the correct Lewis structures. Once we have this done, then we analyze the shape of the molecule based on the arrangement of the electrons around a particular atom. So basically what it is once you draw the correct Lewis structure, you can then determine what the actual shape of the molecule is. There are two ways in which to describe geometries. The first is electronic geometry. That is the arrangement of electrons around a central atom. The second approach is called molecular geometry, which describes the arrangement of atoms within a molecule. The molecular geometry, sometimes called the shape, so when we defer to the shape of molecules, we're looking at the molecular geometry. Depends on the the molecular geometry depends on the electronic geometry, but only considers the location of the atoms. So the molecular geometry, this is what we refer to as the shape, but it's taken from the information from electronic geometry, if that makes sense. So I'm going to read that again. The molecular geometry depends on the electronic geometry, but only considers the location of the atoms. But the molecular geometry is sometimes called the shape of the molecule. So let's begin with a simple molecule. Hydrogen cyanide, which has this Lewis structure, which you can see there. The set bond. I just lost my place again. There are two sets of electrons around the carbon atom. The set bonded to the hydrogen atom and the set bonded to the nitrogen atom. When doing a VSEPR model, we consider the triple bond to be one set. And so basically it's a set. It doesn't matter how many bonds it is. We're not looking at the specific bonds. Think of a single, double, and triple as a set. It doesn't matter what it is. We're not working about the specifics. It's just bonded. So it's a set. When doing a VSEPR model, we consider the triple bond to be one set of electrons, since these electrons all occupy the area between the carbon and the nitrogen. The two electron sets repel each other, so they will move as far away from each other as possible. So think of magnets that have the same side. You can never push them together, meaning they will end up on opposite sides of the carbon atom. The electronic geometry around the central carbon atom is linear. That is, the bond angle between the two sets is 180. As a result, the molecular geometry, the arrangement of atoms, is also linear. As a side note, for simplicity, as we talk about these shapes, we're going to show the central atom in black and the outer atoms in red. In molecular models, we will show single, double, and triple bonds the same way. So when you have three atoms, it's kind of easy to determine the center. But as we get into more complex atoms, one molecule can have different geometries in it because every atom has different bonds. Okay, so let's consider another molecule, carbon dioxide. Which of these geometries would be the most stable? Again, we need to consider the number of electron sets around the central atom. Like our first example, this molecule has only two sets. So again, we're not looking at specific bonds. We're not counting the electrons. We're just counting the they call them electron sets. I just call them attachments. And I use that loosely even for lone pairs. So for me, it's whatever's touching the central atom. So in this case, I would say this is 1, 2, this is 1, 2, 1, 2. If there was a lone pair, there would be 1, 2, 3. I don't look specifically, that's why I don't call it a bond. I just call them attachments, because they are connected in some way to the central atom. And everything revolves, when we're looking at shapes and arrangements, by the central atom. Okay. So like the first example, this molecule has only two sets around the central carbon, And so the most stable arrangement is the one which keeps the electrons as far away from each other as possible. That is the geometry shown in answer C. At any time, the central atom has only 2 electron sets. The electronic and molecular geometry around the atom are both linear with a bond angle of 180. So like the other one, which this compound is 180, carbon dioxide is also 180 degrees from each other. Okay, so let's consider a molecule that has 3 electron sets around the central atom, such as formaldehyde. The central carbon atom has 1 set of electrons bonded to the hydrogen atom, 1 set to the other hydrogen atom, and the double bond to the oxygen atom counts as 1 set. So there, in the way I say it, is there's 3 attachments to the central atom. As before, these electron sets repel each other and so try to be as far away from each other as possible. In this case, the electrons adopt geometry, which we call trigonal planar. In trigonal planar geometry, the molecule is flat. So think of it as flat into the paper or the laptop or computer screen, whatever it is that you're looking at. And each set of electrons is separated by an angle of 120 degrees. If all 3 sets are bonded to the atoms, the molecular geometry again is trigonal planar. The nitrite ion, so I've jumped ahead, here we go. The nitrite ion has 3 electron sets around the central atom. The double bond to the oxygen atom, the single bond to the other oxygen atom, which is in blue, and the lone pair in yellow. The lone pair takes up much more space than the bonded set of electrons, so we must consider it in predicting the geometry of the molecule. The electron sets adopt a trigonal planar electronic geometry. In this example, the electronic geometry and the molecular geometry are not the same. Although electronic geometry is trigonal planar, only 2 of the electron sets are connected to atoms, and so the molecular geometry is better described as bent. So let me explain something here that it's not flat out saying. When we look at electronic geometry, it is the arrangement of electrons around the central atom. If you look over at the molecular geometry, it doesn't count or doesn't acknowledge lone pairs. That's why you don't see it on there. So if you have a molecule that has lone pairs, the electronic geometry and the molecular geometry will not match. They will be different shapes or arrangements. I shouldn't say shapes because that refers to here. But they will have different arrangements. When you have compounds that have no lone pairs on the central atom, the geometries will match each other. When they have lone pairs, the geometries will not match each other because the molecular geometry does not acknowledge the lone pair. So they will be different. And you should expect that if you are looking, when you have to look these up. But the interesting thing about this is that this is bent, but you don't see the lone pairs here. So these are one of these things that's just implied. You have to know. But when they do drawings, this one didn't really show it, but when they show lone pairs, what they kind of do in other drawings is they show like a big rose petal kind of, or petal, because the lone pair takes up so much electronic space. The density of electrons pushes these down because it takes up so much space. Think of somebody sitting next to you and they just push all their stuff around, so you have to move over because they keep putting stuff down on the bench. That's what they're doing. They're taking up more space and it's forcing you to adjust to that. Finally, let's consider a molecule with 4 sets of electrons around it, such as CH4, which is methane. What shape would this take? You might initially guess a cross shape, like a plus sign or a letter X. However, in this geometry, each set of electrons would be separated only by 90 degrees. In fact, the optimal geometry for 4 charge sets is what we call tetrahedral. In this geometry, each set of electrons are separated by 109.5 degrees. So it couldn't be an X shape. The degrees are actually 109.5. In fact, the optimal geometry for 4 charge sets is, again, I think I said tetrahedral geometry. In this geometry, yes, I read that. A tetrahedron can be thought of as an X shape in which 2 of the branches have been turned sideways to create a little bit more room. So that's what they're showing, an X, and then they kind of change it sideways. So it looks more like, I don't know if you guys have, back in my day we had jumping jacks, and they kind of are out like that a little bit. Not exactly, but they, if you don't know what jumping jacks are, you don't worry about it. But that's how these kind of look a little bit. Those had more arms to them. So when it's 4 and no lone pairs, it's usually a tetrahedral appearance. And these are kind of the easiest to get because you're like, okay, lone pair, 4 of them, no lone pair, 4, tetrahedral. And it would be the same for electronic and molecular because there are no lone pairs to it. Okay, so, yeah, so this is exactly what I just said. Because it has 4 sets of electrons, the electron geometry is tetrahedral. Because each set is bonded to an atom, no lone pair, the molecular geometry is also tetrahedral. The tetrahedral geometry occupies a 3-dimensional volume. To show this shape clearly, chemists sometimes draw bonds using wedges and dashes. You will definitely use these in organic, and you will use them constantly drawing if you take organic. The wedge indicates that the atom is coming towards you. The dash indicates it's going away. So let me explain how you envision this. This HCH is in, think of this, I'm looking at my laptop. I don't know what you're seeing this on, but pretend this is a piece of paper, this white. This HCH is in the plane of the paper. It's like typed into the paper, printed into the paper. This dash wedge is pointing directly out. It's pointing directly opposite of you. It's going in the opposite direction. Not towards you, but directly outward. This H here with the dark wedge is directly in your face. It's coming directly at you. So that these are opposite to each other, like in the sense of 180 degrees. So that gives the 3D appearance. When you can't show how something is and you want to indicate it's not flat, that's what we use these wedges for, to indicate that there is a 3D appearance going on here. And it's really easy to draw these in paper or print them out, and you can't catch that with them. So again, the dark wedge indicates the atom is coming directly at you. The dash indicates it's going in the opposite direction away from you, and the HCH that looks normal is in the plane of the paper. So the tetrahedral geometry can lead to more than one molecular geometry. For example, look at the structure of ammonia. Because there are 4 electron sets around the central atom, ammonia has a tetrahedral electronic geometry. However, if we just consider the atoms, the molecule forms a pyramid shape, no lone pairs. We refer to the molecular geometry of ammonia as trigonal pyramidal. So when they're asked about shape, we're looking at molecular geometry. So we would look at this, but we acknowledge that this is the electronic. I honestly don't know why we don't acknowledge this over this, because I think I would want all the information, but I don't write the book, so I don't know. So this is trigonal, like a pyramid. You can see it's kind of pointing and these are all evenly spaced out in a sense. So this is in the plane of the paper. This is coming directly at you, and that one's going directly in the back. In water, in a water molecule, the central oxygen atom has 4 electron sets around it, 2 bonding sets and 2 lone pairs. The electronic geometry of a water molecule is tetrahedral. The 2 lone pairs push the hydrogen atoms towards each other, so the molecular geometry of water is bent. So when they ask about the shape of molecular geometry of water, it's bent. We don't say it's tetrahedral, even though there's 4 connections to water. It is bent, and that's because these 2 lone pairs, if you draw like petals, it's like really big like this, the space it takes up, and this one's really big like that, and it pushes these down. So let's summarize these ideas with the table. If an atom has 2 electron sets, and we're not counting the center, we're looking at it from the view of the center. So we're looking at it from here, we count 1, 2. So if it has 2 sets, it has a linear electronic geometry. Linear central atoms have 2 bonding sets and no lone pairs. So the molecular geometry is linear, and you can see the electronic and molecular match. I'm going to give you a chart to allow you to print it out, and it's going to cover a lot of geometries on there, and it has an example. But this is how you read it. You look at it from the center atom, and then like I said, I don't call these electron sets. I call them attachments because it's easier for some students to understand it that way with a simple word. That we're not looking at lone pairs, we're not looking at bonds, we're looking at what's connected. Or you can even say connections, okay, to the central atom that we're looking at. And again, if we have a compound that has more than one central atom, Then you take one central atom, you look at it and what's connected, then you look at the other central atom and you look at what's connected to that. You break it up into pieces. Okay, so an atom with 3 electron sets has a trigonal planar. The molecular geometry, let me start again. An atom with 3 electron sets has a trigonal planar geometry. There are 2 different molecular geometries possible with 3 electron sets. And if you notice here, you can see that's bonding and bonding. So there's 3 bonds, there's 2 bonds. If there's no lone pairs, these match. If there is lone pairs, then the geometries are going to be different. If 2 of the electron sets are bonding and one is a lone pair, the molecular geometry is bent. The nitrite ion is an example of this type of geometry. If an atom has 4 electron sets, it has a tetrahedral geometry. There are 3 different types of molecular geometries possible with 4 sets. If all 4 electron sets are bonding, then the molecular geometry is tetrahedral, which you see right here. If there are 3 bonding and 1 lone pair, the molecular geometry is bent. Trigonal pyramidal. Trigonal pyramidal. If the 2 sets are bonding and 2 lone pairs, such as water, then it's bent. These are cases in chemistry where there are 5 or even 6 sets of electrons around central atoms. There are cases, However, these main geometries, linear, trigonal planar, and tetrahedral, account for most of the shapes you'll encounter in chemistry. And yeah, there are more, and the chart I'm going to give you is going to have more on there, but these are the main ones that we're going to focus on. It is important to remember these geometries only describe the shape of around one central atom. So this is what I was trying to explain, that we focus on one. So this is one central atom, and then we look at the geometry. We look at this one, we look at the geometry. We look at this one, we look at the geometry. We look at this one, we look at the geometry. And we look at this one, you break them down into steps. And that's how you count it. So a compound can have different geometries throughout the compound. This geometry may not match this one may not match this one, and all of them will have different geometries to them. So it is important to remember that geometries only describe the shape around one central atom. If a molecule contains multiple atoms along the backbone, the geometry of each atom needs to be considered. As an example, look at this molecule. The atoms highlighted with green have a trigonal planar geometry, since they are each surrounded by 3 sets of electrons. These highlighted in yellow have a tetrahedral geometry, since they are surrounded by 4 sets of electrons. Notice that the outer atoms, those connected to one other atom, have not been highlighted. Only the central atoms affect the geometry in the molecule. So we do not consider the geometries of atoms bonded to one other atom. So this has been bonded to only one atom, this is bonded to one, this is bonded to one. So what makes this a central atom? We'll count. It's got more than one bond to it, so you have to include it in the geometry. Lithium carbonate is a simple ionic compound that is widely used to treat bipolar disorder. What is the molecular geometry of the carbonate ion? Although this question does not explicitly ask for a Lewis structure, it is essential for solving the problem. The Lewis structure for the carbonate ion is shown here. Based on this structure, we can see that central carbon atom has 3 electron sets around it, and therefore a trigonal planar electronic geometry. Since all these electron sets are bonded to atoms, the molecular geometry is trigonal planar. And again, it's because there's no lone pairs on the central atom. So let's take a look at some of these compounds that are going to start looking a little bit more difficult. Not this difficult, so these are not something that we're going to really, this is not this level of chemistry yet, but I want you to see them. So let's go through this. This is dopamine. This is the chemical compound, dopamine. Here's adrenaline, ephedrine, and methamphetamine. Now, one thing you need to notice about this is that they all have, in this case, they have this is called a benzene ring. Here, it's a resonance structure. So we have 6 carbons, and then we have some hydrogens, which is actually, technically it's not a benzene ring, but because this should be all hydrogens as well. So let's just focus on the 6 carbons here. They all have 6 carbons. They all have hydrogens on the top and the bottom. And then after that, everything seems to change. Oh, it looks like they all have hydrogens here too. And these are all different positions. I believe this is a meta position is what they call this. I can't remember anymore. It's been a long time. It's not important because that's organic. Anyways, when you start seeing that this is connected out, you see that in this one there's an oxygen, where in this one there's a hydrogen. This one also has a high oxygen, and this one also has nitrogen here. The difference is on these chains here, these end chains, they don't have an oxygen attached. So the base of these are all the same. You can see that they're all the same, except for once we start reaching out, having different molecules, that's going to change the geometry, and it also changes the compound. They all have, so it's similar to, we all have a skeleton, but then we start out, when you start adding the outer layers, we all start looking different, but we all have a foundation that's very similar. For instance, we all have a skeleton. Now, I'm not looking at the complexities of height and so forth, just that we have a skeleton or we wouldn't be able to move. So that's where we start looking at these structures. And that will also get into, all of these would have a different geometry to them because based on what the attachments are on the central atoms. So again, predicting molecular shapes, it's called VESPER. I'm going to put up a chart that's going to have way more geometries than you're going to need on there. And you read it the exact same way. You look at the account, you count the attachments, and then you go from there. Electronic geometry, arrangement of electrons around the central atom. Everything is based on around the central atom. If you have a compound that has more than one central atom, you take it in steps, break it down. But we deal with shapes. We look at the molecular geometry, which does not look at lone pairs. That's why you don't see them drawn, but they're there. This is, they call it electron shapes. I just say attachments, and you count the attachments, and it breaks it down. So I'm going to put this chart up, and mine also has examples on it so you can see. Find the electron geometry and the molecular geometry around each central atom. So let's take a look here. We have 1, 2, 3. This one has 1, 2, 3, 4. This one has 1, 2, 3, 4. So let's take a look here. So we have one that's 3, 4, and 4. So in this case, we have a 3, so it's going to be trigonal planar. And then for electronic geometry, we have 2 that are going to have tetrahedral up here. However, for this one, we have 3, but we have 2 bonding and 1 lone pair. So we're going to go to 3, 2 bonding, 1 lone pair. It's bent. So here we're going to write bent. Here we have tetrahedral, but we have 2 lone pair and 2 bonding. So if we go back up, we have tetrahedral. We have 2 bonding and 2 lone pair. It's bent. And then on this one, we have tetrahedral, and we have no lone pair, or we have a charge on this. So on this one, it's tetrahedral because the lone pair aren't drawn. So we shouldn't, in some of these cases, not, on this one, I would never ask this, to be honest with you. I wouldn't ask something like this because if the lone pair aren't drawn, I would just say it's not there, and I can't specifically state it on this one, but they're saying it's tetrahedral. Okay. So here we go again. This is a compound that has several central atoms, and the geometry is going to look different on this. So we have 1. So we have trigonal planar. 1, 2, 3, no lone pair, they match. Here we have 2. We have 1, 2, 3, no lone pair. So if we have 3, no lone pair, this is also going to be trigonal planar. 4, we have 1, 2, 2, 3, 4. 4 attachments. This is going to be tetrahedral. And this is going to be bent. Why? Because we have 4 attachments, but we have 2 bonds and 2 lone pair, which is going to be bent. And there it is right there. 5 is going to be 1, 2, 3, so it's going to be trigonal planar, because there's no lone pairs. And then 6 is going to be same as this one, tetrahedral, and then bent, because we have 2 bonds and 2 lone pairs. So I put this up in between these so you can see. So what is electronic geometry around 1? Now, electron geometry is interested in lone pairs. However, this doesn't have any lone pairs on it. It's 1, 2, 3, 4. So if we go back, 4 with 0 lone pairs, it's tetrahedral. And I included these in between so you can refer to them. What is electron geometry around 2? So 2 again is 1 and 2, but no lone pairs. So it's got 2 attachments to no lone pairs. It's linear and linear. So they're the same. All right, what is electron geometry around 5? So this is 1, 2, 3, 4. 4 attachments, but 2 lone pair, two bonds. It's going to be, oh, this is asking for electron geometry. So it's not molecular, because I almost said bent. It is 4. It's just four electronic geometry. This one breaks down molecular. But for here, it's just looking at 4 attachments, so it's tetrahedral for electronic geometry. So I almost made a mistake on that one. Oh, here we go. Hold on. Did I miss up? Okay, yeah. So here's 5. It's asking for tetrahedral. Just counts the attachments. Doesn't care what type. And that's what the chart's showing. But if we break it into molecular, it's bent because there's 2 bonds and 2 lone pair. And that's what it's asking for in this one. So make sure you understand which geometry it's asking for, and you're looking at the correct chart. Here's electronic. Here's molecular. What is the molecular geometry of CCl4? This is a pretty easy one. I didn't put it up here, but it's a carbon with 4 of the symmetrical Cl atoms and no lone pairs. I already knew this. I didn't draw it out on purpose. Some of these you need to actually start drawing out. If you haven't, you should have more than enough made attempts to be drawing Lewis structures out. This is a tetrahedral. These are usually the easiest because they're just all, it looks like this. What is the molecular geometry of a molecule whose central atom has 1 pair of electrons and is bonded to 3 other atoms? So this is asking for the molecular. So let's count this. We have 1 and 3. So we have 4 sets. So we're here. It would be electronic tetrahedral. But it's saying it has 1 pair of electrons, so 1 lone pair, and 3 bonds. So in that case, it's here. It's trigonal pyramidal. It looks like this. There it is. Which of these has a trigonal planar molecular geometry? So this is trigonal planar. So this is where you're going to have to draw these out to see if you have a lone pair or not. The lone pair is going to give you a trigonal pyramidal answer. If it doesn't have lone pair, it's going to be trigonal planar. So I found this. It's a resonance structure of this, and it's nitrate ion. The H and H bond angle in the molecule below is closest to, again, this is where you look at Vesper. 1, 2, 3, 4, 4 attachments, but 3 bonded and 1 lone pair. And it is closest to 109.5. I think the one that I'm going to put up also has the degrees on it. This one doesn't have degrees. I don't like that it's asking questions but not giving you guys the degrees. What is the molecular geometry around the highlighted carbon? 1, 2, 3, 4. This is very easy. No lone pairs, 4 attachments, tetrahedral. Those are the easiest to count. Which of these has a trigonal pyramidal molecular geometry? It's very easy. The one that has a lone pair. If you can find the lone pair, then you're going to find the one that looks like that. And there you go. Which of these has a linear electronic geometry? That means 2 sets and no lone pair. And that would be